Okay, Chiwi. So we start with this chapter, nuclear physics, and the topic is radioactivity. This is P4 topic. Now, if we have any atom, its proton number represented by Z and the mass number represented by A. Usually, if proton number in the nucleus is greater than 83, or the mass number in the nucleus is greater than 200, then the atom or the element is known as natural radioactive. Now, due to this natural radioactive process, the nucleus is unstable. For stability, it emits radiations named as alpha, beta, and gamma. So when the proton number is greater than 83, mass number greater than 200, the atom, the element, the nucleus is unstable. It is the natural radioactive. For the stability, it emits radiation like alpha, beta, and gamma. And the number of nuclei in the element decreases, which is called decay. So decay is the process of radioactivity. So number of the nuclei decreasing during the radioactive process is called decay. And the number of radioactive nuclei decreasing per unit time is called decay rate. And this decay rate is represented by delta N over delta T or dN over dt. And this decay rate is also called activity and represented by A. So activity is dN over dt. Now, number has no unit, time has second. So 1/2 for the activity or the decay rate is called backward, which is represented as capital B, small q. So the decay rate and activity is represented by A, and it is measured in backward, mean if one nucleus, one atom decays in 1 second, then the activity will be 1 backward. So activity or decay rate will be 1 backward if one atom, one nucleus decays in 1 second. For example, we have uranium 92-238. After the emission of the alpha, it is converted into thorium. So uranium is decaying into thorium. Similarly, when this uranium 238 emits beta, it is converted into Neptunium. So after beta decay, uranium is converted into Neptunium. Your uranium numbers decreasing, but this thorium or the Neptunium increasing. So uranium is called parent nucleus, and thorium and the Neptunium, they are called daughter nucleus or the nuclei. So activity is equal to dN over dt. Now this radioactive decay, number one, is random, and number two, it is spontaneous. Random mean we cannot predict about this radiation process, how many radiations will be emitted, which nucleus will decay next, and at what time the next radiation will be emitted. So these three are unpredicted. So this is called random behavior. I mean, we cannot predict about the nucleus, which nucleus will decay next, how many radiations will be emitted next, and at what time it will be emitted, that they will be emitted. So this behavior is called random. And spontaneous behavior is the rate of emission of the radiation, mean the decay rate or the activity does not depend on any surrounding physical condition, mean change in temperature, change in pressure has no effect on the rate of decay. So this property is called spontaneous. For example, we have 1000 number of the uranium atom. After one half-life, 500 decays and 500 remainings. After second half-life, 250 decays and 250 remaining. So here, the decay rate is 500 divided by half-life, and here the decay rate dN over dt is 250 divided by half-life. Half-life is constant, so look, dN over dt decay rate is decreasing with number of nuclei. As the number of the nuclei decreasing, so activity, decay rate is also decreasing. So we can write activity directly proportional to N, or dN over dt directly proportional to N. I mean, N is the number of the undecayed nuclei present in the sample. Now, A is equal to some constant lambda n, or dN over dt is equal to lambda n. So this is the formula for the activity, and this is for decay rate. So same, because activity is dN over dt. Now from this, we can write dN over n is equal to lambda dt. And this dN is actually the decrease in the number of the radioactive nuclei. And this is the total number of the radioactive nuclei present. So dN over n is called probability of nucleus to decay, because this is the total number and this is a decaying number. So this is called probability of the nucleus to decay. So the probability of the nucleus can be calculated by the multiplication of this decay constant and time t. So probability of any nucleus is lambda times t. But what is lambda? What is this decay constant? It can be written as dN over n divided by dt, mean we can write this decay constant is the probability of any radioactive nucleus to decay per unit time. So it is the probability of any radioactive nucleus to decay per unit time. This is called decay constant. Now, the probability has no unit, the time second. So this decay constant lambda is measured in second power minus 1. Activity is 1/2, but measured in backward. This decay constant is 1/2, but it will remain second power minus 1. Now, the formula is dN over dt is equal to lambda n. Look, dN over dt is equal to lambda n, but actually this number of the radioactive nuclei is decreasing with time. First 1000, after one half-life 500, after second half-life it becomes 250, and so on. So it's decreasing. So we can write dN over n is equal to minus lambda t, and this minus sign is showing the trend. Now, we can integrate it according to the mathematics. When the quantity has derivative over there, it is ln n. And this can be written as minus lambda t plus integral constant. So you have to remember only this formula. Now, when time taken is 0, mean at the start of the experiment, the start of the observation of the experiment, the number present in the sample will be considered the original number. Hence, when we will put here the time 0, then we have to substitute this n naught. So C is equal to ln n naught. Then the equation becomes ln n minus lambda t and this constant ln n naught. Now, this is not required in the A-level physics. So we will write this equation ln minus ln n naught is equal to minus lambda t. So according to the log rule, we can write ln n over n naught is equal to minus lambda t. So ln over n naught. When this ln shifted over here, it becomes minus lambda t, e power minus lambda t. So this derivation is very, very important. Now the question is, what is n naught? N naught is the number of undecayed nuclei at the start of the experiment. What is N? N is the number of undecayed nuclei after time t seconds. And what is lambda? Lambda is decay constant. Lambda is decay constant. So t is the time. Now, n minus n naught or n naught minus n will be the number of radioactive nuclei which are decayed. N undecayed left, N not undecayed present at the start. So the difference will be the number of the radioactive nuclei decayed. Now, this can be written as N is equal to N naught E minus lambda T. Now, according to the previous equation, activity directly proportional to n, and definitely the number depends on the mass. When the mass is more, definitely the number of the nuclei, number of the atom will be large. When the number of the atom will be large, the activity will be large. When the activity will be large, so the sample will emit more number of the radiations per unit time. So the count rate will be large. So these four physical quantities, these four quantities are directly proportional to each other. So mass N, A, C. What is M? M is the mass of the sample. N is the number of the atom present in the sample. A is the activity, mean the rate of decay. And C is the number of radiations emitted per unit time, which is called count rate. So we can write C divided by C naught, A divided by A naught is equal to N divided by N naught is equal to M divided by M naught. But what is N naught, M naught? So M naught, N naught, A naught, C naught are actually the number, mass, activity, count rate at time 0, and CAN after time t. So look, N over N naught is E minus lambda t. So these four equations are equal to E minus lambda t. So we have four relation, C over C naught, E minus lambda t, A over A naught, E minus lambda t, and N over N naught, E minus lambda t, and M over M naught, E minus lambda t. Okay, suppose at time 0, the number of the radioactive nuclei present are N naught. And if the time is past equal to the half-life, so definitely half of the number decayed and half remaining. Then according to the formula, N is equal to N naught E minus lambda T. If this T is substituted with the half-life, then N naught E minus lambda, if the time is half-life, then this N will be the half of the N naught. So N naught cancelled. So left side is 1 by 2, and the right side is minus lambda but half-life. So when ln is taken both side, 1 by 2, ln of E minus lambda half-life, ln 1 by 2 is minus 0.693, and this becomes minus lambda half-life ln E. ln E is 1, minus cancelled. So the product of the decay constant and the half-life for all radioactive nuclei is constant, which is 0.693. It means the half-life is equal to 0.693 divided by lambda. So this is the formula for the half-life. 0.693 divided by decay constant is equal to half-life.